Yeah, so we'll just wait for like 2 3 more minutes, allowing everyone else to join, and then we'll start. Yeah. Right. Can you hear me and see me?
Yeah, we can hear you.
Okay, cool. So, good evening, everyone. We'll be starting the session now, right? So, the subject of the session is, the maths behind the ML models or any algorithms. So, we'll just get into it. Second, let me share screen. Right. Okay, is the screen visible?
Yeah, we can see.
Yeah. Okay. So, good evening once again. The session topic is unveiling maths behind ML. So, what will we be covering today? So, the reason why I wanted to take this session mainly is because like any ML session you generally see, they just like have some like code along session type thing where they just cover the code and then you just write it code. You have an ML model, it predicts, it works. But you don't understand like the maths or the how the algorithm works underneath the code, right? So that's what I thought would be a good topic to talk about for today. So what we'll be covering today. Right, first I'll just talk about how maths is important in general, and then we'll be covering these four algorithms and talking about how maths plays a part in their algorithm, how you calculate the cost function, hypothesis, etc. So let's get into it. Why is maths important? Right, so maths plays a crucial role in any algorithms, right? Not just CS. It can play chemistry, science, anything in general, right? And the mathematical concepts of calculus, linear algebra, and probability theory are very important just to design algorithms, especially in computer science, but in any field in general. So, for example, you use probability theory and Bayes theorem in naive Bayes, which is a classifier which you use, which is another ML model. And calculus you use in calculating the cost function, the gradient descent, and all, which we'll see soon. So basically, what I'm trying to say is a solid understanding of these, mathematical concepts, or a strong foundation is necessary if you're looking for a career in, ML, data science, or in general also maths is pretty useful. Yeah. Okay, so the first model we have is a linear regression. So before I get into it, I just want to briefly explain what a linear regression is. I mean, I'm assuming a lot of you would already know. So a linear regression is basically just a type of supervised learning, right? So you will have like this group of points which you see here, and then the whole objective is just to get like the best line which fits this group of points, such that the cost is minimum, which we'll be seeing later. So just if you see this group of points, you can assume the best line would be something like going in between these lines, right? Obviously, it will not be going through all the points because this is a linear regression, meaning that the line that we get will be linear. So obviously, it cannot go through all the points perfectly through, but you can kind of get like some middle ground between the points, and that would be a good estimate of the predictions of what values we can put, right? So what is a hypothesis? A hypothesis is basically a predicted value, like how you are predicting your value, right? So I'll just run you through like a simple linear regression, which will just have like one feature, and then I'll show you how it works for like multiple feature thing, right? So if you look here, uh, h of theta is basically the hypothesis function, and it's dependent on the parameters which you have. That's why we write h of theta. So h of theta is equal to theta 0 plus theta 1 into mileage, right? So this is a single feature because mileage is your only feature in this hypothesis, and the system, the what we're trying to predict is basically like the car price. So for example, right, I have this. So this is an example of a simple linear. So this is your input feature, the mileage. So you have 186, this. Obviously, this is a very simplified data set. You will not get data set this good looking anywhere, but assume, just for explanation, right? So this is your input feature, what it looks like. And so based on this input feature, you need to calculate some predicted value, right? So this is your actual value. You will get like some predicted value which you will calculate, and then you will evaluate the model by calculating the difference between your predicted value and your the actual values. And also, yeah, another thing which I forgot to mention is why is this called a supervised algorithm? It's called a supervised algorithm because, like, in the training data set that we have, you have labeled data. What do you mean by labeled data? Labeled data means that you are kind of telling the model what you want. So, for example, this is labeled data because you're giving it like some output. You're saying, okay, for this is the output. For this is the output, and then predict similar output results for new examples. Another example would be like me. This could be like instead of the output being the car price, right? It could be whether the car will sell. Okay, so that would be like one meaning yes it will sell, zero meaning it will not sell. So that could also be an example of supervised because you're saying okay, if it's 18,186,000 kilometers, then zero it will not sell. If it's 19,200 kilometers, then yes one it will sell. Similar to that. That's why it's called label. And unsupervised is when you don't have this output column at all. You just have the input features, and then it's up to the model to try to find like some sort of similarity or some sort of collinearity, or something which is common, or some details about the data set, right? So that is what unsupervised algorithm is, which we'll be looking about at later. Okay, right. So yeah. Okay. So if you look here, you have, and generally we do this with matrices because it becomes easier to process the whole thing. We call it like vectorization, where we have a vector is basically like a matrix of one dimension. So this is an example of a vector. This is an example of a vector. This is a vector. This is a vector. Right? This is a vector. So how this works is, right, is okay. So you would know basic matrix multiplication, I'm assuming. So how this would work is, if you were to multiply these two matrices, you would get theta 0 into 1 plus theta 1 into 186005. So I took these values from this to kind of, so that you can relate and actually see what I'm talking about, right? So this, it will calculate this value, right? So it will do theta 0 into 1 plus theta 1 into 186005. It will get some value, and that is your predicted value. I gave is equal to, just to show you like the structure of the matrix, what it will look like, but it will not be actually 133828. That is like the actual value. What you will get with this multiplication is like the predicted value, which is h of x, h of theta, right? So if you look here, you will get a similar expression or formula or whatever. So you can see hypothesis of x is equal to theta transpose x. So theta here is like your parameters, right? So you can kind of relate this to like a linear, it's linear regression, right? So you can relate it to a line. So this formula h of theta is equal to theta 0 plus theta 1 into mileage can be related to as y is equal to mx plus c. So this here is y, this is m, mileage here is your x, your input feature whatever, and theta 0 is your intercept, which is c. So you have y is equal to mx plus c. So that's how it works, and this is how it works for a single feature example. Right. So do you have any questions so far? Please feel free to ask. Otherwise, I'll move on to multiple feature. Yeah. Okay. No questions. Right. So I'll show you how it extends to multiple. Okay. Yeah. So this is how it would extend to multiple features. So here, over there, we just had one feature, which was mileage. But here we have, one, two, three, four, five. We have five features. Wait, just delete this. We have five features, right? We have five features, and this is your output, which you need to, predict. So if you look here, you will see that this has four features, not five. Don't get confused. This is not five features. This theta 0 is just the intercept. It is not like a feature of its own. It's just like if you look here, it's multiplied with one. It's not multiplied with like some input feature. It's just multiplied with one. So here you have four features, which is theta 1, theta 2, theta 3, theta 4. And if you were to perform this matrix multiplication, you'll get like theta 0 into 1 plus theta 1 into 2010 plus theta 2 into 0 plus theta 3 into 3.5 plus theta 4 into this value 186005, and you will get some predicted value with that, right? Which will come over here. It will not be 133828 like I said. I'm just doing that so that you understand how the matrix, final matrix will look, right? And then if you do this for the second example, which is 1201103192000, you will get this value. And then if you do this for the third, you will get this value, right? So that's how it works. And I just showed this for like, four features and three examples, but in reality you will have like far more features and far more examples. So you'll have like, maybe 10,000 examples and like maybe 50, 100 features. So this, the matrix will get like very complicated. So it's important you understand like how the matrix works exactly, because very, very easy to get confused because you'll not know where the one is coming. So yeah. Okay, next slide. Okay, so what is a cost function, right? So any algorithm that you have in ML, mostly it will have like some cost function. The cost function is something that you use to evaluate a model to see if it's doing, to see how it's performing. So if you have like suppose one iteration of a model, then you do some changes, it becomes a different iteration of a model. You can compare the two values of the cost function to see whether the model has improved in performance or decreased in performance. I don't know the word, but yeah, decreased in performance, right? So this is what the cost function looks like for a linear regression. So it is j, which is j is the cost function. It's dependent on the parameters theta 0, theta 1, and it's equal to 1 by 2m, the sum of squares of the difference between the predicted value and the actual value, right? So I'll explain this to you with, so a few slides back, yeah, we had this image, right? So if you look here, this red line over here is your predicted value, because it's the line that you have drawn, and then these blue points over here are your actual values, right? So what you do is, so if I were to just calculate like the cost value function, the cost function value of this graph right here, right, with this prediction, what I would do is, suppose this blue dot over here is at 18 and this red line over here is at 14. So the difference between these two vertically is 4. So you'll take that 4, you'll square it, like you see here. So it's hypothesis we have predicted, so that would be 14. 14 minus yi is your actual value, which is 18. So 14 minus 18, 4. You square it, so 4 square 16, and then you do it for I is equal to 1 to m. So m is your number of examples. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you do it for all these 10 examples. You sum the square of it, and then you divide it by m, which is the number of examples. So you get like a kind of average, average difference. So it's exactly this, is the average difference between the hypothesis and the actual values. And why we have a 1 by 2, you'll see later when I explain like the partial derivative part. You'll see it's used to like cancel the square part. You'll see that later, right? So once you have like a value of a cost function, the whole objective is to minimize this, the value of the cost function, because like an ideal situation would be where the cost function is 0, which is not possible in most cases, but that's like the ideal situation, right? So you want to reach as close to 0 as possible. You want to, reduce, right? Okay, so here we had the j, and we were getting that value of j based on some values for the parameters. So how do you calculate the parameters to become better parameters? To become parameters wherein the value of the cost function will decrease. So we use a technique called like gradient descent, where what you do is you update the parameter values until the cost function reaches like its global minimum value. So if you look on the right here, this is like the formula, right? So this is for single, so it's j is equal to 0 and j is equal to 1. So what you will have is theta j is equal to theta j minus alpha. Alpha is the learning rate, and this is the partial derivative of the cost function by, theta j. So for example, this is theta 0. It will be theta 0 minus alpha 1 by m. Okay, so this part I'll show you. So basically it's theta 0 minus alpha into this part, right? So how do you calculate this? If you remember, wait, I think it's here. Yeah, right. So it's here. So basically the partial derivative of g of theta, which is 1 by 2 hypothesis of x minus y whole square. So if differentiation, what you do is x to the power n, the differentiation is n into x to the power n minus 1, right? So this 2 will come in front, and 1 by 2 that you had from here, this will become 2 to the 2 into, this x to the power n minus 1. So n minus 1 is 2 minus 1, which is 1. So you just have hypothesis minus y, and then you have the partial derivative of this part, which is this, and then you get this basically. So remember the two that I was talking about. So this two gets cancelled with this two to give you this function. That's like the whole point. I mean, it's not very significant, but it's there, right? Okay, so that's how you change your value of your parameters. So if I were to show you this thing, right? Okay, so if you look at this, can I hold on? Okay, so if you look at this diagram, right? So you'll have to like initialize your parameter to some value. So suppose 1 1, then it will calculate the j, and then it will update the parameters to get a lower value. So it will become like suppose 0.5 and 0.3. Then it will calculate again. It will see, okay, update it again to maybe 0.5 and 0.3. And then eventually, these are like steps that it took, So it was initially 1 1, then it became 0.5, 0.3, then it became 0.1, 0.5, and then slowly, it will reach like the global minimum of the cost function. So this is like the cost function, and this is your parameter theta 1 and theta 0, right? So if you look here, you have two, I mean, you have two local minimums and one global minimum. So, for example, if assume that this was a global minimum, if you started the initialize the parameters here, it will go and get stuck here. It will never come here, because this is a local minimum. It will just think, okay, this is the global minimum. I'll just stop the algorithm here. So choosing where you initialize the parameter is also kind of important. Like there are algorithms for that. I'm not remembering the name, but there are algorithms for choosing where to start off your parameters so that you ensure that it ends up at the global minimum. Okay. Yeah, and so I told you about the alpha, right? So this alpha over here. So this alpha is called the learning rate, and it basically talks about how big or small the updation to the parameter is. So if you look here, so theta j minus, if alpha is a very big value, right? So if it's suppose this value, right, this partial derivative value is 1, let's assume for simplicity, right? And alpha is 2. So this will be, it will reduce the value by 2 into 1. So 2. But if alpha is like 0.1, it will do 0.1 into 1. So it will reduce the value just by 0.1. It's significantly decreasing the amount of, how big of a step the parameter took. Okay. So why is this important? So you basically have like three cases, right? One case is where your learning rate is very big. Okay. So okay, first I need to explain this graph, this curve to you, right? So it's basically xy. X here is your parameters, and y here is your cost function. Okay. So initially, suppose this yellow point was the start, right? It will, what it does is it will calculate like the tangent to this curve. Okay, it will calculate this. It will calculate like the slope of this. Okay, and then it will subtract it. So basically, this theta, right? This theta is here, and then it will subtract it from this. So obviously, this tangent over here, right? The slope of this is positive, so it will go minus. It will basically reduce the value. Is what I'm trying to say. It's not very clear, but that's what I'm trying to say. It will reduce the value. Okay. So once it reduces the value, it will reduce the value further, and it will go like this. So you may ask, what about if it accidentally comes like here, what if it's starting over here, won't it just go back? That will not happen. Why? Because suppose you have a, you're initializing here, right? And then you will take the tangent, which will look like this. So obviously this tangent is negative, right? So if this tangent is negative, what you get is it will become theta j is equal to theta j minus of something, so it will become theta j plus, meaning that this theta j which is here, it will become like a greater value, so it will go here only, right? So it's not a big issue. Okay, now if you choose a learning rate which is too big, what will happen is it will take too big of a jump, right? So it was supposed to come here, but it took too big of a jump, it went on the other side, and then again it will take too big of a step, so it will go there, and then it will become divergent, meaning that it will never reach like the global minimum. Your goal is to reach here, but you just get increasing cost values, which is not what you want. So that's what happens if it's too high. If the learning rate is too low, what will happen is it will take very small steps towards the global minimum. So this will take like a long time. I mean, eventually it will reach the global minimum, but it will just take like way too much time, so it's not really worth it. So what you want is like in between this, it's in between too low and too high, it's like just right, where it's fast enough to take decent steps, but it's also not too big that it will become divergent. So that is what learning rate is. Does anyone have any questions? Please let me know if any questions. No. Okay. So we'll move on to the. So that is a linear regression. Now we'll go on to the second algorithm which I wanted to talk about. So we have the logistic regression. I'm similar to linear regression in some way. It's just different in. So again, it is a supervised algorithm. I explained what that is, and the difference in this, right, from a linear regression is that a linear regression output can be continuous. It can be like 1010.0.3. I mean, not 0.0.3, but 0.03 and anything basically. But for a logistic regression, the output can only be in like a certain number of values. So, for example, classification can be binary, or it's also called classification, by the way, and it can either be binary or multi-class. Binary meaning that it has two output classes, so usually which is 0 and 1, or it can be multi-class. Multi-class meaning that suppose you're trying to predict what number is on an image, the output for that would be 10. It would have 10 classes. The 10 classes would be like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's your 10 classes, right? So it can be multi-class also. So how it works basically, right, is it it considers like a threshold value. So normally speaking, this is 0.5, but I think you have to change it depending on your situation and what value you think would be really good for the use case. And then values above the threshold value will be considered as one output, and the output value for that will be one, and below the threshold value the output value will be zero. And this is basically, so this green line here is called a decision boundary. Yeah, you can see boundary here. So why it's called a boundary is because it separates like the positive cases from the negative cases, like the outputs having one and the outputs having zero. That's basically what decision boundary means. Okay, so this is the hypothesis, as I explained, how you basically predict your uh, how you calculate your predicted value. So in logistic regression, what you do is you just take like the sigmoid function of it, right? So G here is your activation function, and what it takes is your theta transpose x, which if you remember is basically it will give you one value. It will do like the matrix multiplication of the parameters and the input, and it will give you one value. So you take that one value, right, which is z over here, and then you plug it into the sigmoid function, which will give you an output, and that is your final output, right? So the basically the formula for g of z is 1 by 1 plus e to the power minus z. If the graph, yeah, this is the graph, right? So it's an S-shaped graph. This is the sigmoid function, and why this is very like useful is basically what it does is it takes like any value of x, right, any value for this z. So this can be like anything, it can be 10, it can be 100, it can be 500.3.4, right? So it takes all of those values and it converts it to a value which is between 1 and 0. So all of these values, they lie between 1 and 0. So obviously this is asymptotic in the sense that it will never actually reach 0, it will just tend towards 0, and here also it will never reach 1, it will just tend to 1, right? So, as I said, it helps to convert a function with arbitrary values to a value between 0 and 1. Now, why is converting the value between 0 and 1 important is that you want to basically classify these into either yes or no, right? So, what you normally do is you say, okay, so, the hypothesis was j of z. So, suppose my value was 6, assume, right? So, the sigmoid function gives me a value somewhere here, right? So that value is above 0.5. So generally what people do is like they take 0.5, and if your point is below 0.5, you consider it no or 0, and if it's above 0.5, you consider it 1 or yes. Okay, so if your point was here, it is above 0.5, you consider that as a yes, 1. So as you can see here, if hypothesis is greater than equal to 0.5, y is equal to 1, and if hypothesis is less than 0.5, y is equal to 0, right? Oh, okay, also this is pretty good. Okay, so if z is equal to 0, remember z is equal to this part, and okay, you don't even need to remember that, just remember this: g of z is equal to 1 by 1 plus e to the power minus z. So what, so if your z is equal to 0, right, if z is equal to 0, this becomes 1 by 1 plus e to the power 0, which is 1 by 2, 1 by 1 plus 1, right? So 1 by 2, which is 0, so this value, so you can see here like 0, 0.5, it makes sense, right? And then if z is tending to infinity, so if z is somewhere here, right? So if z is infinity, then it will become 1 by 1 plus e to the power minus infinity. So that means 1 by 1 plus 1 by e to the power infinity, which will become e to the power infinity 1 plus e to the power infinity, which is, infinity by infinity, which is 1, can kind of say, not exactly, but yeah. And then for the opposite case, which is minus infinity, what happens is 1 by 1 plus e to the power minus of minus infinity. So it becomes 1 by 1 plus e to the power infinity, which is 1 by infinity, and 1 by infinity is 0, you can kind of say. So that's how you get these three equations, which I have put here, So that's how you work that. Okay. So like I said, the cost, I showed you the cost function for linear regression, but I'll show you the cost function for logistic also. So this is the cost function for logistic. It is minus 1 by m, and you do this operation for all m training examples, right? All m training examples. So I just made like a simple table so that if you don't understand this, you can kind of understand what's happening, right? So this is like the predicted value which we predicted, and this is the actual value. So if both the predicted and actual values are same, the cost, or the cost whatever, it will be zero, because you have actually correctly predicted it. It's perfect. And for similarly for 1 1, the cost function will be zero. But if not, so for example, the predicted value, you predicted 1 but it's actually 0, what will happen is, if you look here, so yi is your actual value, so yi is 0, so this whole part becomes 0, and then this part you're left with, so 1 minus 0, and this part, so, and then you take the minus from here, and then minus log of, minus 1 minus yi into log of 1 minus hypothesis of that. And then on the other hand, if you predict is 0 but it's actually 1, in that case this will become, this half will become 0, because it will become 1 minus y, this will become 0, and then you just have this, which will be added to the cost, which is minus yi into log of hypothesis x. So in case I forgot to mention, xi is basically like your input feature for the ith training example, and yi here is like your output for the ith training example, and generally if you see like a number below the I, it means like the exact feature of that particular training example. So that's what it means. Okay, any questions for logistic regression? I thought this. Yeah. Yes.
For logistic regression purposes, we have seen the equations for only two classification purpose. So what about if there are multiple classes?
No, if there are multiple, there will definitely be like, I don't have the function here because it will become like very long. But obviously there will be like a cost function and all, which it will get like, if you predict it wrong, maybe like the gap will be different or something. Like I've not researched into that deeply, but for example, if you predicted one but it was actually four, uh, maybe like the difference, if you like the cost will be greater if the actual value was 9 and you predicted 1, then if the actual value was 4 and you predicted 1, like the cost might be bigger because your value is like so off. It's you should be penalized more in that sense. So that would be what the cost function, it will definitely be there. Like if I search for it, it will be there, but for now I just thought I'll keep it simple and show like just binary. So this is just for binary. So good question. Like this is just for binary classification. You can obviously have multi-class classification as well. So does that answer the question? Yeah. Oh, Harsh.
Uh, yeah, so I was asking, can
Yeah.
we find local minima from linear regression cost function?
Yeah. So you can apply gradient descent to this again, wherein you will like update the value of the parameter, and then you will get, so this will all, so you will get like a situation where like the gradient descent will give you such a good parameter set that it will always correctly predict, so it will reduce the cost function that way. So there is definitely a way where you can use gradient descent, or some other like techniques are also there, but usually people just use gradient descent because it's easy, it's intuitive, and most of the time it reaches at the global minimum. I mean, sometimes it gets stuck at the local minimum, like we saw here, but most of the time it goes into the global bin. Is that okay?
Yeah.
Yeah. Thank you. So we move on. Right. So the third one, right, it's called k-means clustering. So basically, it involves creating clusters from data, and it has many applications, especially in fields like marketing and customer segmentation. Okay.
So my question is regarding to the logistic regression and our linear regression models, like the classification models. So K-means clustering and the logistic regression are both classification models. So whatever may be the superposition method, but in both the methods we are able to distinguish a group of clusters, no? Basically. हाँ हाँ हाँ. Yeah. So talking about the efficiency, which model will be better in terms of clustering this value and why?